Welcome to the video on heat engines. A heat engine is a device that converts heat to work, such as a car engine, a power plant, or the human body, or it may convert work to heat, such as a refrigerator or a heat pump. In this video, we will primarily discuss converting heat to work, but the same principles that we discuss would apply to both applications. By the end of the video, we will have discussed what determines the efficiency of a heat engine and why principles of thermodynamics provide a fundamental limit to this efficiency. As a basic example of a heat engine, let's consider a car engine. So here's the engine in the car, and then it gets heat by burning fuel. So we'll just say that is the heat into the engine from burning fuel in this case. And then also it has heat coming out. So this is heat that is lost to the environment. We would prefer that the engine does not generate any, but it will. So this is the heat out. And of course what we want the engine to do is to move the car. And so that would be the work that is done by the engine. So we'll call that work out. Say to move the car. So this is the basic picture of what's happening. Ideally, we would like 100% of the heat in to be converted to useful work. This would make the car engine 100% efficient and would require that the heat out right here be zero. Before we go further, let's be clear on the terms work and heat. Both of these terms represent a transfer of energy to or from the system. In this case, the system is the engine. But they do it by different mechanisms. Work transfers energy by applying a force over a distance, and of course we use a W for work. Heat transfers thermal energy as a result of a temperature difference. For instance, when you put a cold cup of coffee on a hot plate, heat is transferred from the hot plate to the coffee cup. We use a Q to represent heat flow. Here is a common schematic that we will use to show the work and heat associated with a heat engine. So here's a hot temperature source, here's of course our engine, and then a cold temperature source down here. And so the heat would flow from the hot temperature source. So there's the Q symbol for heat from the hot one, and then from the engine flowing into the cold temperature source down there. And then we want our engine to do work, and so schematically, again, like we did in the previous picture, this is the work done by the engine. And terminology-wise, up here, TH, this is the hot temperature reservoir. And then down here, TC is the cold temperature reservoir. We will assume that the temperature reservoirs are large with a large heat capacity so that their temperatures don't change as heat is transferred into or out of them. As we discuss the efficiency of the heat engine and investigate how efficient it can be, we will also use some idealized scenarios to simplify our analysis and to allow us to find the fundamental limitations of efficiency due only to the principles of thermodynamics and not due to other factors such as friction that would factor into an actual engine. Let's begin by considering a piston in a closed system. So by closed, we mean that matter, the gas inside the piston in this case, cannot be transferred in or out of the system. But energy can be transferred by heat or work. The figure shows a piston in position A filled with a gas, which we will assume is an ideal gas. The gas has properties such as temperature, pressure, and volume. If the gas pressure is large enough, it will force the piston to move up to position B like this. In position B, the volume of the gas has clearly increased, and the pressure and temperature of the gas may have changed as well. These three variables are related to each other by the ideal gas law, which is commonly written these two ways, where lowercase n is the number of moles, uppercase N is the number of molecules, R is 8.31 joules per mole per Kelvin, and Kb is the Boltzmann constant, which is 1.38 times 10 to the negative 23 joules per Kelvin. It is a common and useful practice to plot a process like this on a pressure volume or PV diagram, where pressure is on the vertical axis and volume is on the horizontal axis. I have plotted where states A and B might be on this PV diagram. As the piston moves and the values change, the path might look something like this. We will discuss this path in more detail later. One of the useful features of a PV diagram is that we can use it to indicate the amount of work that was done by the engine, in this case by the force of the piston as the gas expands. To show you how we can do that with a PV diagram, let me simplify this scenario a bit by making the pressure constant as the piston expands. This makes the path from A to B horizontal like this. For a constant force, work equals force times distance times cosine of the angle between those two vectors. And then we can recognize that pressure in general is force divided by area. And so let's solve this for force and plug it into the other equation. So that would be pressure times area. So we'll substitute that in here. And so then the work equals the pressure times the area times the distance and the cosine of theta. So the piston is pushing up on something external to the piston, something in the car perhaps, to make it move, and the piston is moving in that direction. So here's the displacement vector as it moves up like that. And so those two vectors are in the same direction. These are vectors. And so the angle between them is 0. So we can go ahead and set that angle to 0, and the cosine of 0 is just 1. And we can also recognize that AD here is the change in the volume in the gas, so delta V. So let me show you that here. So here's there's D, and then this is the area is the top of that piston there, and so A times D is the volume that the gas increased. And so work in this case is pressure times the change in the volume. Well, P times the change in the volume, it's the area under the curve that we just drew. Area under the curve. So here's the area under the curve. And so therefore, this is the magnitude of the work that is done by the engine. So this can be generalized for all processes. So for example, in the path I drew originally, the magnitude of the work then is the area under this curve. The sign of the work can be seen from the equation, which was work equals the pressure times delta V. If the volume here increases, then delta V is positive and the work done by the system, that is to say the engine, is positive too. Or if the volume decreases, then the work done by the system is negative. Or you could say that the environment does positive work to the system. So to summarize, work is the area under the curve in the PV diagram. If the volume increases, the system does positive work on the environment. If the volume decreases, the system does negative work on the environment, or in other words, the environment does positive work onto the system. In our example, the piston extended and the volume increased, as shown by the arrow that I drew on the path right here. So the piston did positive work. Now, as a practical matter, any engine must return back to its original position so that the process can be repeated over and over and over. So we might show the piston in position A and then B and then A again. On a PV diagram, this cyclical process might look like this, where the arrows indicate the direction that the process is going, in this case from A to B and then back from B to A. Notice that the engine is doing positive work from A to B, represented by this area, and negative work from B back to A, represented by this area. The net or total work that the engine does after a complete cycle then is the difference between these two areas, or in other words, the area that is enclosed by the circular path here. From this analysis, you can see that it wouldn't be useful for the engine to follow the same path back from B to A that it took from A to B, because then the areas would be the same, and so the net work done by the engine after a complete cycle would be 0. So we've talked about the energy being transferred to and from the system via work and heat. Because energy is conserved, these transfers of energy must change the internal energy of the system. This, in fact, is what the first law of thermodynamics says. The change in the internal energy equals the net heat added to the system minus the work done by the system. The negative is on the work because when the system does positive work, energy is transferred out of the system. A few comments about internal energy. Internal energy of a system is based on the kinetic and potential energies of all of the atoms or molecules in the system. Temperature is essentially an average of these energies, so in the end, internal energy is directly proportional to temperature. The specific equation is this: internal energy equals 3/2 N, the number of molecules, times the Boltzmann constant, times temperature. Temperature can also be replaced using the ideal gas equation, so that equation just becomes 3/2 times pressure times volume. When we discuss the state of a system at any instant in general, we can think of the state in one of two ways. One way is to use the microscopic view of the system, as we just did, and discuss the state of all of the individual particles, that is to say the atoms and the molecules. Another way, though, which is often more convenient, is to discuss the variables that essentially describe the average of all of these particles. The variables that describe the state of the individual particles are variables like velocity and position, and referred to as microscopic variables. The variables that describe the state of the system as a whole are macroscopic variables, which includes pressure, volume, temperature, and the internal energy that we just talked about. As an example, let's consider the system we were discussing a moment ago that is initially in state A and transfers to state B. When P and V are plotted for one of the macro states like A or B, all of the macrostate variables such as temperature and internal energy are also defined. We can see this for temperature from the ideal gas law. Say PV equals the Boltzmann constant times temperature. And so knowing PV, we would then be able to determine what the temperature is. And we can see this for internal energy from the equation internal energy equals 3/2 times P times V. And so obviously knowing P times V, we would then know the internal energy. Notice that the macro state variables P, V, T, and U define the macro state of the system at a state like A or B, but they do not say anything about the transition between A and B. This means the macrostate variables such as P, V, T, and U depend only on their location on the PV diagram and are independent of the path between those states. Conversely, work and heat, which are not macrostate variables, only depend on the path between the states. To make this point, we know that work is the area under this curve from A to B, but the work back from B to A would be the area under this curve. So clearly, work is different for the two paths, and so work is path dependent. And if work is path dependent, then heat must be too, which we can see from the first law of thermodynamics. So let's write that down, and let's solve that for the net heat. And so if work here depends on path, well then mathematically, so would the heat. It is important to realize that we can only describe the macro state of a system when the system is in thermodynamic equilibrium. For example, if we say that the pressure of the system when it is in state A is 500 psi, then it should be 500 psi throughout the system, or everywhere in the system. And this idea would apply to all macrostate variables. This will be an important issue in a moment when we discuss what the actual path is for a system as it transitions from one macro state to another. Okay, so recall that our goal is to determine the maximum efficiency of a heat engine. To do this, we will analyze an idealized process called a reversible process.